My dear students, we'll continue with the design. So, in the previous two sessions, I have covered output equation and choice of specific magnetic loading, choice of specific electric loading, main dimensions, short circuit ratio, effect of SCR on machine performance, calculation of length of air gap. Now today, this armature design also discussed. Okay, and today we'll start with field system design. Today we'll discuss field system design and calculation of MMF per pole at no load and normal voltage. Next, design a field winding for salient pole alternator and rotor design for turbo alternator, that is non-salient pole rotor. So coming to design of field system, we'll see design of rotor of a salient pole machine. So first we'll see how to find out dimensions of pole. So flux in the pole body phi p is equal to leakage coefficient and useful flux per pole. This pi is the useful flux per pole and this is the leakage coefficient. Okay, so in the flux body, whatever the flux is there, all the flux will not reach to the air gap. So some leakage flux will be there. So that you have to multiply. It will be more than 1. That is CL is equal to 1.15 to 1.2. So now area of cross section of pole body AP is equal to pi p by BP. Usually BP is equal to 1.5 to 1.7 Weber per meter square. Now for square pole AP is equal to BP into LPI. So where net iron length of the pole is LPI is equal to L into KI. Taking length of the pole LP is equal to L, armature pole length. BP is width of the pole. K is the stacking factor, usually 0.98. L is armature length. For circular poles, AP is equal to pi by 4 dp square. This is the dp is the diameter of the pole. dp is the diameter of the pole. This is the square pole. Okay, this is BP into LP. This is the area for square pole. So now we'll find out, once you find out width and length, we'll find out height of the pole. So now to counterpart armature reaction, the ratio of field MMF divided by, that is field MMF to armature MMF. To counterpart armature reaction, the ratio of field MMF to armature MMF, that is ATFL by ATA, that is equal to 1.7 to 2. Means ATFL should be very large. Because of armature reaction, there will be a demagnetizing effect, there will be a cross magnetizing effect. So to counterpart the armature reaction, the ratio should be 1.7 to 2. Where the armature MMF ATA is calculated using this equation, 2.7 IPH by A TPH KWP. A is the number of parallel paths. IF is the current in the field winding, AF is the cross sectional area of the field winding, TF is the total number of turns in each field winding. RF is the resistance of each field coil. RF is the resistance of each field coil. Okay. So because the number of field coil depends upon number of poles. So this RF represents resistance of each field. Now LMTF, the mean length of the turns of the field coil. DF is the depth of the field winding, usually 30 mm to 50 mm. It is selected from the data book based on the rating of the machine. Rho is the specific resistance of copper, 2 into 10 raised to minus 8 ohm per meter and mm square. HF is the height of the field winding. SF is the copper space factor, 0.6 to 0.8. QF is the specific heat dissipation, that is 700 to 750 watts per meter square. S is the surface area of heat dissipation. So now here, in finding out the height of the field winding, what we'll do here, we'll find out copper loss, and that loss has to be dissipated from the surface of the field coil. So what is the heat dissipating surface area? Okay, that equation we have to write. Again, multiply with QF, that is specific heat dissipation. So equating these two, we can find out the height of the field winding. So now we'll see copper loss per coil. This is equal to IF square into RF. This is I square R. IF square, this is the RF, rho LMTF by F in watts. Moreover, total copper area in the field winding is AF into TF. That is cross sectional area multiplied by number of turns. This will give actual copper area. This is also equal to SF dF into QF. So this is not QF. This should be HF. This should be HF. This should be HF. Okay. SF dF HF. Okay. So this the depth and height. This also gives total copper area, actual copper area, but it contains insulation. It contains insulation. That's why you have to multiply with SF. Okay, SF is the space factor, copper space factor. If you multiply with this one, this usually SF is 0.6, less than 1, 0.6 to 0.8. So if you multiply this one with SF, it will give actual copper area. Actual copper area. That's why SF is called copper space factor. Copper space factor. Now AF is equal to DF HF SF divided by TF. This is equation 2. This is equation 1. Okay, this is equation 2. Now substituting 2 in 1 we get, okay, now IF square rho LMTF into TF DF HF SF. So this comes out to be IF into TF whole square rho LMTF DF HF SF watts. This is equation 3. Now as I told, we have to find out total loss dissipated from the field coil. So this is equal to QF into S is the surface area through which heat is dissipating. So now cooling surface area, here neglecting dF, that is depth of the coil, S is equal to 2 LMTF into HF, 2 LMTF into HF. Now hence total heat dissipated, S if we substitute here, QF into this 2 LMTF HF. This is equation 4. Now for the temperature range of the field coil to be within the specified permissible limit, the copper losses in the field coil should be equal to the losses dissipated from the coil. Then only temperature will be maintained within the permissible limit. Whatever the heat generated, it has to be dissipated into the surface area. So now equating 3 and 4, we get IF into TF whole square is equal to rho LMTF divided by DF HF SF is equal to this 2 LMTF into HF into QF. So therefore from this height of the coil is equal to substituting rho, so IF TF divided by 10 raised to 4 root of SF DF QF. This is equal to, if we take 10 raised to 4 minus 4 here, is IF TF will be ATFL root of SF DF QF. Once you find out height of the field winding HF, height of the pole is given by HF plus 0.03 meter. This is for insulation, clearance, etc. Okay, this derivation already we have discussed in DC machine. Only thing you have to remember this equation. This equation is important for solving the problem. Okay. Now coming to depth of the rotor core. So flux in the core section pi c is equal to half of the flux per pole. So now this is equal to half of the leakage coefficient CL into pi. Now the cross sectional area of the core is equal to pi c by BC and also equal to LC into DC. So from this DC, okay, can be found out, DC can be found out. Okay, so now DC is equal to AC by LC. See this AC you have found out using this one. So now AC by LC. Here LC is approximately equal to LPI, net iron length of the pole. So here, while calculating EC, DC we have to assume 1.0 to 1.2 Weber per meter square. Assume this. This we have calculated using this equation. So you can calculate EC. Once you calculate EC, this we know. Okay. So LC, this we can calculate using this equation. So DC can be obtained using this equation. That is the depth of the pole. Now I'll come to magnetic circuit. Okay. Calculation of MMF per pole at no load and normal voltage. See the figure here. Okay, this is the pole body. This is pole shoe. This is a yoke, rotor yoke. This is rotor yoke. This one, it is called hub also. Okay. Now this is stator teeth. This is stator teeth. This is core. You can see the depth of the core. This is length of the LC. Okay, flux path in the core. Okay. So this you can see depth of the slot here. Depth of the slot. Depth of the slot. Okay, this is the length of the air gap here. The depth of the yoke, like that. So now the magnetic circuit figure below, which shows that the magnetic per pair of poles comprises of yoke, pole and air gap, armature teeth and armature core, shown below. Okay, shown below here. Okay. So now it means that the flux passes through the pole body, pole shoes, air gap, stator teeth, stator core and rotor core. So now total MMF per pole at no load and normal voltage is equal to ATF naught is equal to ATG ampere turns required to push the flux through the air gap and to push the flux through the rotor teeth. This is teeth and teeth of the stator. This is the stator core and this is the pole body and this is the yoke. This is the yoke. Okay, yoke of the rotor, this one. Okay, ATY. So now see, we'll find out one by one. First, we'll find out MMF required for air gap of silent pole machine. So ATG, so that is given in terms of ATG, that is ATG is equal to, this is the standard equation, 8 lakh BG kg LG, where kg is the gap contraction factor, BG is the maximum flux density, BG is the maximum flux density, LG is the length of air gap, LG is the length of air gap. Okay, this is small LG. Okay, this is gap contraction factor. Okay, now MMF for teeth is equal to ATT into DS. So DS is the depth of the rotor, that is the armature slot. So depth of the teeth is equal to depth of the slot. Okay, ATT, where ATT MMF per pole corresponding to flux density at 1/3 height of the from the narrow end, and DS is the depth of the slot. So what we have to do, we should find out flux density at 1/3 height from the narrow end of the tooth. Okay, corresponding to that flux density, we should find out ATT from the BH curve, or BAT curves. Once you get this ATT into this ampere turns, this is in terms of meter, multiply with DS, that is in terms of meter, ATT per meter, multiply by this DS in meter, you will get ampere turns, total ampere turns. Now similarly, coming to MMF required for armature core, ATC is equal to ATC, okay, into LC. This is a total ampere turns for armature core is equal to ampere turns per meter for core multiplied by length LC. Okay, flux path. This is the LC in flux path in the armature core, where ATC is MMF per pole corresponding to flux density in the core. Okay, and length of the flux path is core is taken equal to 1/2 of the pole pitch on the mean diameter. Okay, this LC, length of the flux path in core, is taken as pi. Okay, D, this is the diameter. After that, 1 ds below, on ds on top, 2 ds, dc by 2 on top, dc by 2 in the below, divided by 2p, divided by 2p. Okay, LC can be found out using this equation. Substitute here. This corresponding to flux density in the core, we should see what is the ATC, ampere turns per meter. This is in meter. This is ampere turns per meter. This is in meter. Meter gets cancelled. You will get finally total ampere turns. Now coming to MMF required for the pole body, that can be calculated using ATP, capital ATP is equal to small ATP max into HPL by 3 plus ATP minimum into 2 HPL by 3. Okay, this is the ampere turns required per meter at maximum flux density. This is for minimum flux density. Okay, so now we'll see why we are using HPL by 3 and 2 HPL by 3. What do you mean by 2 ATP max and 2 ATP minimum? So we know that the flux in the pole body is not uniform throughout its radial length. It is assumed for the calculations that the 2/3 length of the pole carries the useful flux plus the leakage flux between the pole shoes while bottom 1/3 length carries useful flux, the leakage flux, both pole shoes and pole bodies. Okay, 1/3 carries useful flux. This is useful flux. Okay. So now here the 2/3 length of the pole carries the useful flux plus leakage flux between the pole shoes, while bottom 1/3 carries only useful flux. Okay. Thus the flux at the pole top is minimum. The flux at the pole top is minimum, while at the bottom is maximum. Okay, this is the pole. Okay. Now this is the useful flux. Now here windings are there. So some leakage flux will be there here only. This is due to this winding. Understand? So here maximum flux will be occurring. Here minimum flux will be occurring. Okay, this is because only useful flux is coming from this pole surface, where ATP is the MMF per meter corresponding to flux density in the pole body. So using this equation, find the flux density at 1/3 height and 2/3 height. Corresponding ATP max and ATP minimum you have to find out from BH curves. Okay, and multiply with HPL by 3. Is there 2 HPL by 3? You will get MMF required for pole body. Okay. Now coming to MMF required for rotor yoke, ATY is equal to small ATY, ampere turns required per meter for corresponding flux density in the yoke, that is for the rotor hub, multiplied by Ly. So ATY is the MMF per meter corresponding to flux density in the yoke. Ly is the length of the flux path in the yoke. Okay, pi dr is the rotor diameter. From that you subtract 1 HPL in the top and 2 HPL in the 1 HPL in the bottom. That's why it is called 2 HPL minus 2 HPL, and dy by 2 on the top and dy by 2 in the bottom. So that's why minus dy divided by 2p. So once you know flux density in the yoke, find the ATY from the BH curve, multiply with this Ly using this one. So you will get ATY. Now therefore, total MMF per pole at no load and normal voltage is calculated using this equation. ATF0 is equal to ATG, ATT, ATC plus ATP plus ATY. ATF0 is equal to ATG plus ATT plus ATC plus ATP plus ATY. Okay. Now resistance of the coil RF is equal to rho LMTF is rho LMTF by AF. Okay. So now we'll see once again this something wrong with the recording. We'll see once again. We'll start with the design of field winding for salient pole alternator. So this already we have discussed in case of DC machine design, in the DC machine field winding design. Okay, this field winding is designed for 80 to 80%, 85% of exciter voltage. 15% is given for the variation in the field current, that is drop across rheostat. So thus voltage per field coil EF is equal to 0.8 to 0.85 V divided by P. P is the number of poles. Since all the poles are connected in series, field windings are connected in series. So whatever the voltage, applied voltage input given to the field winding divides across each field winding. So that is the reason we have to divide it by P. Assume depth is equal to 0.03 meter to 0.05 meter from data book depending upon the rating of the machine. So to calculate LMTF is equal to 2 LM. Here you can see 1 LM here, this side 1 LM. This is the thickness, this is the field wind DF, this is BF. Okay. So using this equation we can calculate LMTF. Where LM is equal to 0.9 L, E is equal to 0.05 L. Okay. So now Ti is the thickness of insulation wrapping on pole. Now resistance of the field coil RF is equal to rho LMTF TF. Rho LMTF TF. So this also we have RF is equal to EF by IF. So this equating this and this. Okay. Now EF, if you take this side, okay, EF I will take this side, EF this EF you take this side, EF you take this side, IF you take this side. Then finally cross sectional area of the conductor EF is equal to rho LMTF IF TF by EF, rho LMTF ATFL EF. So assuming delta F in the field winding to be 3.5 to 5 amps per mm square, the field current IF can be calculated using this equation. Once you find out IF, okay, number of turns you can easily find out. TF is equal to ATFL divided by IF divided by, this is ampere turn. If you divide it by ampere, you will get turn. Find out the actual value of resistance of the field coil depending upon this TF. So rho LMTF into TF divided by AF. So copper loss is equal to IF square into RF. So this loss is to be dissipated by the field coil to maintain the temperature within the limits. So heat dissipating surface of the coil is equal to 2 LMTF into HF plus DF. So temperature rise is equal to QF theta, temperature rise theta is equal to QF CF divided by S, where CF is the cooling coefficient. So you can find out temperature rise by substituting CF here, where VA is the, here VA is the peripheral velocity. Okay. If temperature exceeds the limit, increase the depth of the field winding. Which increases the cross-sectional area of the conductor. And hence reduction in the current density. In the conductor leads to the reduction in copper loss. Finally, coming to rotor design of turbo alternator, that is non-salient pole rotor. So turbo alternators are usually used in thermal power stations or nuclear power stations. So turbo means the speed is very high. So in that case you cannot go for salient poles. So for that, because whenever machine speed is high, large amount of centrifugal force will be acting on the body. So you cannot go for salient poles. Usually turbo alternators are having low diameter, and length will be large. So in case of turbo alternators, the rotor winding is not concentrated. The rotor winding is not concentrated, but distributed in rotor slots. Distributed in rotor slots. You can see here, these are the windings distributed in rotor slots. It is not concentrated. Like usually in pole, okay, windings, it will be concentrated in, around the pole, but here it is distributed. Here it is distributed. Concentric multi-turn coils are used to show, which is shown in the figure. The number of wound slots should be multiple of 4. Multiple of 4. To avoid undesirable harmonics, the slot pitch should be chosen properly. Normally, 70% of the rotor is slotted and remaining portion is unslotted in order to form the pole. So this is 70% are slotted. This is unslotted. These are the unslotted. So this will form poles. This is behaves like a south pole. This is acts as a north pole. This has impact of south pole. This has impact of north pole. So these winding arrangements are like that. So here current ending, current leaving. Because of that, this acts as a south pole. So now here left side current entering. Okay, here this is plus here, so it acts as a north pole. Here this one, this is plus, this is minus. Okay, because of this winding arrangement, they create impact of north and south pole. So this is actually rotor, this one stamping. There is no physical poles are existing. There is no physical poles are existing. Because of this, this is unslotted this portion. Okay, this is slotted portion. Here windings are arranged. The windings are embedded. Because of that, it behaves like a north and south pole. North and south pole. So you can see here, this is unslotted area. This is slotted area. This is overhang. Okay. So current density in the rotor winding is assumed to be 2.5 amps per mm square. Now coming to design, full load feed MMF ATFL is equal to 2 times armature MMF. 2 times armature MMF ATA, where ATA is equal to 2.7 IPH TPH kW by P. Okay. So feed MMF has to be made large to overcome the armature reaction. Okay. Now let V be the exciter voltage. Voltage across each feed coil EF is equal to 0.8 to 0.85 into V divided by P. Again, length of mean turn is calculated using this empirical formula 2L 2.32 plus 2.24. So where tau is the effective span of the coils, P is the number of poles. Now resistance of the coil RF is given as rho LMTF TF by AF. Also RF is given EF by IF. So equating this and this, EF by AF is equal to rho LMTF TF by AF. Similarly, the cross-sectional area of the conductor AF is found out using this equation. Already we have found out. Okay, rho LMTF ATFL by EF. Okay, where IF is the field current, TF is the number of turns in the field coil, LMTF is the length of mean turn, rho is the resistivity ohm per meter mm square, EF is the area of field conductors in mm square. Okay, now you have found out cross-sectional area AF. Now total area of the field turns. So this is cross-sectional area, number of turns multiplied by number of poles. Now we are finding out total area of field turns in a rotor. Now total area of field conductors. So conductor is, if you want, turns has to be multiplied with 2. Okay, 2 AF TF P. Now coming to total area of field conductors. Total area of field conductors. So now here AF I have substituted here IF by delta F. So now 2 ATFL, this is IF into TF is ATFL into P divided by delta F. Since delta F is equal to IF by delta F, that I have substituted. This implies IF is equal to delta F into AF. Okay. Assume suitable value of current density in the field winding with respect to cooling techniques. That is 2.5 to 3.3 mm for conventionally cooled machines and 8 to 12 amps per mm square for large and specially cooled machines. Specially cooled machines. Now, once you find out IF, assuming delta F, because AF you have found already you have calculated. So delta F, assuming this one, IF is calculated. Once you find out IF, the number of field conductors, is calculated using this equation. So this is ATFL per pole multiplied by number of poles into 2. This will give total number of conductors. Total number of conductors here. Okay. Total number of conductors. So now this this 2 into P into ATFL. This will give the total number of field conductors. Okay. Now divided by IF. Divided by IF. Divided by IF. Okay. So now this this will give 2P ATFL divided by IF is a delta F by AF. Okay. So now if you want number of field turns TF, so turns you have to divide by 2 conductors, whatever the conductors you are getting, you have to divide by 2. So this 2 gets cancels. This 2 gets cancels. So P into ATFL by IF. So P into ATFL by delta F into AF. Okay. So now once you get TF, you can find out actual value of RF. RF is equal to TF into rho LMTF. Rho LMTF divided by AF. Substitute here TF. Okay. So again revised value of field current IF can be found out. Actual value of field current is EF by RF. Whatever IF you are getting, you substitute here divided by this one field current you are getting. So now therefore conductors per slot is equal to 2 into P ATFL divided by delta F AF divided by SR. SR is the number of wound slots in the rotor. SR is the number of wound slots in the rotor. So like that, number of conductors per slot you can find out. Resistance of the field coil, cross-sectional area of the conductor. Okay, like that you can design the non-salient pole rotor in case of turbo generator. Okay, this finishes the design of three-phase synchronous machine. Okay, in some of the problems, we are supposed to find out pitch factor Kc and distribution factor Kd. So they will not be directly giving the values. Okay. So Kw, usually Kw is equal to what? Kw is equal to Kc multiplied by Kp. Multiplied by Kp. So sometimes they will not be giving Kw directly. So for that we should find out Kc and Kp and find out Kw. So now to find out pitch factor Kc, so this equation is cos alpha by 2. What is alpha? Alpha is equal to angle of short pitch, or that also equal to beta slot angle multiplied by number of slots by which coils are short pitch. Or also alpha is equal to 180 minus actual coil span of the coil. So this is how alpha can be found out. Substitute here, Kc can be found out. Now distribution factor, okay, can be found out using this equation. Kd is equal to sin q beta divided by 2 q sin beta by 2. Q is the slots per pole per phase. Beta is the slot angle given by 180 by n. N is the slots per pole. N is the slots per pole. Okay, use this equation, or distribution Kd can be used using this equation also. Kd is equal to sin theta ps divided by 2. Theta ps is phase spread. Okay, Q is slots per pole per phase. So distribution factor Kd is equal to sin theta ps by 2 divided by Q sin theta ps by 2Q. So as I told, theta ps is phase spread and Q is slots per pole per phase. So using this we can find out Kd. Later we can find out Kw. Okay. So this completes the design of three-phase synchronous machine. So in the next class, we will see how to solve the problems, and some of the problems has been solved. What are the methods, how to approach, how to anticipate the design problem, we'll see in the next session.